You know that graphics card humming away in your PC? We all think we know what it's doing. But what if I told you that deep down, inside the silicon itself, there's something else, something completely unexpected? We're talking about a secret, analog brain.
So when you think about your GPU, you're probably thinking about pure digital power, right? It's all just ones and zeros, running code with perfect precision. But what if that's not the whole picture? What if that's only half the story?
Well, according to some really groundbreaking research, it's not even close. The answer is a hard no. Turns out that digital world we see, it's just the surface, a carefully built facade.
Because underneath all that clean digital logic, there's a whole other world, a chaotic, kind of messy, but unbelievably rich analog world. We're talking about real physics, fluctuating voltages, tiny hot spots of heat, little timing jitters, all the stuff engineers usually try their best to stamp out.
And here's the kicker. The researchers behind this basically said, hey, what if all that mess isn't a bug? What if it's a feature? They figured that if you could just get around all the normal software layers, the drivers and firmware, you could tap directly into that raw physical world.
Okay, so that's the big idea, which of course leads to the next question. How on earth do you do that? How do you hack into the silicon itself? This is where things get really, really cool.
I mean, think about it. How do you actually peel back the layers on a commercial GPU? These things are designed to be black boxes. How do you get in there and actually listen to the whispers of the silicon?
All right, so this is basically the treasure map the researchers drew up. It's like peeling an onion to get to the GPU's physical core. So up at the top, layer 4, that's the surface level, what most developers use. It's the HIP API, it's clean, it's digital, it hides all the messy hardware stuff. Now you go one layer deeper to layer 3, and you're at the instruction set level, using assembly language. Getting closer. But the real magic, the big breakthrough, happens at layer 2, MMIO, or memory mapped I/O. This is like a secret backdoor straight to the GPU's guts, totally bypassing the drivers. And it gets even crazier. Layer 1 uses something called the System Management Network to read raw sensor data, like actual temperature and power readings. And layer 0, that's the firmware, totally locked down. But those layers in the middle, that's the playground.
Let's just pause on that layer 2, the MMIO, for a sec, because this is the key to the whole thing. It lets the scientists read the GPU's internal state super fast, like 100 million times a second. This isn't like making a normal software call. No. This is like putting a stethoscope right on the heart of the chip and listening to its raw, unfiltered heartbeat in real time.
And here's the really mind-bending part. All that stuff we've been talking about, the power fluctuations, the heat, the timing jitters, everything we normally call noise and try to get rid of, well, with this kind of deep access, it's not noise anymore. It becomes a signal, a useful structured signal you can actually compute with.
And look, this proves it's not just random static. What you're seeing here is basically a frequency analysis of that noise. See how each of those lines has a different slope? That's showing that the heat noise from one layer has a totally different character from the timing jitter from another layer. Each one has its own unique physical fingerprint, and that fingerprint carries information.
So, okay, it has a fingerprint, but is it actually useful? Oh yeah, look at this. They ran a test classifying some simple waveforms. That tall bar there, that's the result they got when they fed the raw power noise from the GPU into the system. It blows the other results out of the water, especially the one with no noise at all. The physics, the actual raw physics of the chip, is making the computation better.
Okay, so let's recap. We found the secret analog world inside the GPU, and we know it's not just noise, it's actually useful for computing. So, what do you do with it? Well, the first crazy idea they had was to build a bridge.
Think about how we normally do this. If you want your digital computer to talk to an analog thing, you need a translator, a digital controller that turns ones and zeros into analog waves. It works, but it's clunky. This new method, it throws the translator out the window. It's like letting two native speakers talk directly to each other. No interpreter needed. Just two analog systems, the GPU and another chip, speaking the native language of physics.
And who was the GPU talking to? A brain-like, neuromorphic chip. It was basically a simulation of 128 spiking neurons, the kind you have in your actual brain. So they took the raw physical noise from deep inside the GPU and piped it directly into these artificial brain cells.
And you guys, this is where the story goes from cool to absolutely mind-blowing. Because when they connected these two analog worlds, something incredible happened. They saw the system spontaneously organize itself into a state that many scientists think is the key to all complex computation.
It's a state called self-organized criticality. A cooler name for it is the edge of chaos. And it's exactly what it sounds like. It's the perfect sweet spot for any complex system. You don't want it to be too rigid and orderly, but you also don't want it to be pure random chaos. This edge is the perfect balance, and it's where real, powerful computation happens. So what happened when they fed the GPU's natural physical noise into that brain-like chip? It pushed the entire system 27 times closer to that perfect edge of chaos state.
And this chart just lays it all out. See that dotted line at 1.0? That's the target, the perfect edge of chaos. Now look at what happens when you feed it just generic random white noise. That's the bar way over on the right. The system goes totally haywire. But then look at the bar for the GPU's physical noise. It brings the system right up to 1.027, almost dead on perfect. It's the specific structure of the GPU's natural noise that does it. That's the secret sauce.
So the big takeaway here is pretty clear, right? When you combine these two different analog systems, this hybrid approach, you create something that's way more powerful than either one could be on its own.
This chart says it all, really. Just look at that first set of bars for memory capacity. You've got the FPGA on its own and the GPU on its own. But when you bridge them together, that's the bridge bar, the capacity just shoots up. The whole is literally greater than the sum of its parts.
But wait, because the research has one last twist, and honestly, it's the biggest one. It turns out the GPU doesn't even need the other chip. The GPU can be a neuromorphic, brain-like computer all by itself. You know those weird quirks programmers hate, like memory bank conflicts or branch divergence? Well, they're not quirks. They are physical, predictable effects, and you can use them to compute. By only using its own internal physics, the GPU hit 97.7% accuracy on a classification task. And the craziest part? It was 100% repeatable every single time.
So what this really shows us is that we're surrounded by these incredible devices, and we've basically just wallpapered over their true physical nature with layers and layers of clean digital abstraction. This research just ripped a hole in that wallpaper. And it leaves you wondering, right? What other secret, powerful worlds are lying dormant inside the technology we use every single day, just waiting for someone to look beneath the surface?